Okay, so Francesco Mattiotti got his master degree in physics in Brescia in 2016, working on interplay of cooperativity and noise from light harvesting complexes to quantum transport, and working with Borgonovi and Luca Celardo. And then he got a PhD in collaboration between Brescia and Notre Dame, working on cooperative effects in quantum systems, super radiance and long-range interactions. And since 2021, he's a postdoc at the University of Strasbourg in the group of Guido Pupillo. And today, Francesco is going to give a talk with the title Strong Light Matter Coupling in Disordered Systems, Multifractality and Protected Transport. Thank you. Francesco, you have 25 minutes.
Thanks a lot to Società Italiana di Fisica e Statistica and for allowing me to give this presentation. Here we'll try to put my work into context to connect it with previous works of my current group and that I've done with my PhD. And in the last part, I will show a little bit of the new things that I'm doing here in Strasbourg. So before starting, I would like to thank my collaborators in my group, our leader Guido Pupillo, director of the European Center for Quantum Sciences, and the CNRS researchers, Johannes, David, and our collaborator, Jérôme in Nancy. So the general topic where I can locate my work is it's optoelectronics, let's say. That is the conversion of light into electric current and vice versa. This process typically involves the creation and the motion of excitons. And here I will mostly focus on organic materials where excitons are the type of Frenkel excitons, so with a very small Bohr radius and not strong binding energies. Exciton motion in this media happens through a process called the Foster resonant energy transfer, or FRET, that works by recombination of an exciton and emission of a virtual photon that is reabsorbed at a given distance with a probability that scales as the dipole-dipole coupling at that distance. So this is a short-range process, and it's very sensitive to disorder that can come from inhomogeneities or impurities in the material. This leads to exciton recombination, and this lowers strongly the efficiency of optoelectronic devices. To overcome this problem, the idea is to try to engineer somehow long-range exciton hopping, and one way to do this is to use the electromagnetic field that is naturally extended over optical wavelength, confining it into an optical cavity. This idea has been proposed, for example, in this pioneering work more than 20 years ago, where it has been shown that Foster FRET transport between a donor and an acceptor material can be modified when the materials are placed inside an optical cavity. And it's what's important to point out here is that this experiment has been done in a regime where the coupling to the cavity field is weak compared to the line width of the cavity and of the material. So the question is what happens when the coupling is instead strong? And this has been analyzed, for example, in the group of Thomas Ebbesen here in Strasbourg, where it has been shown that when one considers a layer of a donor material and an acceptor material separated by a given spacer whose thickness can be tuned, if one looks at the decay of the population of the donor material, when the whole system is placed inside a cavity, the decay rate is affected just by the presence of the cavity that is created simply by depositing two metal layers on the two sides. And importantly, the speed up here in the decay rate is shown to be robust when the spatial thickness is increased up to tens or even hundreds, close to hundreds of nanometers, which is a regime where standard threat transfer becomes irrelevant. Now, the localized nature of the electromagnetic field can also have some effect when it's not confined in a cavity, so when it's in open space. An example is the phenomenon called superradiance, which is a situation where one has a bunch of emitters of the same kind in an order array disposition within a volume that is smaller than the emission wavelength of the material. In this situation, the spontaneous emission happens cooperatively, and the spontaneous radiative decay rate is increased by a factor of n, where n is the number of emitters. This has been observed in different physical systems, and for example, here in quantum dot superlattices quite recently. So an important thing here is that the observed speed up here in superradiant emission is much smaller than what one could theoretically expect, and the reason, as we have shown here, is that even if the number of collectively coupled elements is very large, the coupling to the light field in open space is still weak, and so the system is strongly sensitive to disorder and thermal noise, even if this experiment has been done at 6 Kelvin, so at very low temperature. So it's important to consider light field confined inside an optical cavity to try to make collective coupling to the extended field stronger and more robust to disorder and noise. Now I would like to introduce a toy model to describe exciton transport under strong coupling to a light field. This is basically a Tavis-Cummings model with the addition of an near-Steiner hopping. So in detail, I have a collection of n two-level systems that are described by these pseudo spin half objects. A single mode cavity described by this boson and resonance with the spins, collective coupling between light and the spins, and a nearest neighbor hopping term that describes normal short range thread process. This Hamiltonian can be looked and diagonalized in Fourier space. One observes that there's a special mode called the bright mode at zero momentum that represents all the spins synchronized with the same phase, which is the only one coupled to the photon field. The coupling strength is this collective coupling term that depends on the density of elements inside the cavity volume, and this is the parameter that we are going to keep constant when we do scaling analysis of the system. Together with this, we have n-1 dark modes that are decoupled from the cavity field, and their dispersion is given simply by the nearest neighbor hopping term in this case. In single excitation, then the spectrum is characterized by the hybridization of the photon mode with the bright mode, and so we have the creation of these hybrid light matter states called polaritons that are two and separated by a Rabi split in twice omega c. Now an important question already arises, because if all the cooperativity is concentrated in these two states, the two polaritons that are extended, then the amplitude of on each single site is just a factor 1 over n, the squared amplitude actually. So the question is, how can local observables, like the ones that are relevant to transport, be affected by this small 1 over n term on their sides? Now, one ideally would like that also all the n-1 dark modes should enter into play and play some effect into the coupling to the light field. And as we are going to show, the ingredient that allows this effect is static disorder. Disorder comes from heterogeneities in the system, and we are going to model it by adding randomness in the transition frequencies of the spins. So now the photon mode is at resonance with the average of the spin frequencies, and they are taken from a uniform distribution with the width W, so that W represents the disorder strength. Now, in the first part, I'm going to focus on the single excitation regime, and in the last part, I will show some results when the excitation density is finite. Now, just to recall, in absence of coupling, of the coupling to the light field, we just have the standard famous Anderson model that in the single excitation is characterized by eigenfunctions that are exponentially localized in a real space with a localization length that decreases with the disorder strength. In 1 and 2 dimensions, all eigenstates are localized for any finite disorder strength, and so transport is exponentially suppressed as a function of the system size. In 3 dimensions, we have a metal insulator transition, so when disorder is strong, we are in an insulating phase with eigenfunctions localized on neighboring, on few neighboring sites that happens to be at resonance. And this can be characterized by looking at the level statistics, so the distribution of neighboring energy levels of the system, which in this localized phase follows a Poisson distribution. On the opposite regime, when disorder is weak, we are in an extended metallic phase, so the eigenfunction can be delocalized over an extensive number of sites, and the level statistics is in this case following a Wigner-Dyson distribution. At the critical point between the metal and the insulating phase, the eigenfunctions in the Anderson model are multifractal. To characterize multifractality, one needs to introduce a quantity called the inverse participation ratio that tells information about the distribution of the probabilities of a given eigenfunction psi alpha over the site basis. Now, at criticality, the system is a scale invariant, which means that if I divide the system in small boxes of a size small l, the inverse participation in this case only depends on a single given scaling factor, which is the ratio of the box over the total size of the system. In particular, here we have a power law dependence of the inverse participation ratio over the scaling factor. And multifractality, in particular, is characterized by the fact that this exponent in the power law dependence is a nonlinear function of the parameter Q that characterizes the inverse participation ratio. Multifractal phases are also often characterized by a semi-Poissonian level statistics that has both level repulsion similar to the Wigner-Dyson statistics, but also exponential tails similar to the Poissonian level statistics. So it's a hybrid in this sense. Now, what happens when we have an Anderson localized system coupled to a cavity field? First, let us look at what happens to the states in the Fourier basis, because when we introduce disorder in the system, together with the terms that we have analyzed before, now we also have a scattering term that couples all the dark modes to the bright mode. So basically, this allows all the dark states to be coupled to the photon state via the bright state. And this allows all of the Fourier modes of the system to acquire a non-zero amplitude on the photon state, so a non-zero photonic weight. Even if this photonic weight scales as 1 over n, we have now an extensive number of states in the system that are coupled to the photonic weight, and so we can expect, and as we're going to show, we can see some effects of these on the local transport properties of the system, and this is one of the key ingredients in this. We'd like to just mention that this mechanism of disorder giving a finite photon weight to the dark states has been seen experimentally. Here in this setup in EPFL, ultra-cold lithium atoms have been placed inside a one-dimensional optical lattice. And as one can see that if you measure, and the optical lattice is coupled to a resonant Fabry-Perot cavity. In absence of disorder, the transmission through the optical cavity shows only 2 peaks that correspond to the polariton hybrid states of the system, and the transmission at frequency 0 here is vanishing because the dark states are decoupled from the light field. But as disorder is increased, we see the appearance of a non-zero cavity transmission at the frequency of the dark states. So we actually see that the dark state become gray and acquire a finite photon weight. Now, how do these gray states, or I will call them dark states for convenience, look like? If we look at a single disorder realization, they are typically characterized by a small number of large amplitudes over a few sites that can be at an arbitrary distance between each other. So basically, the cavity induces some long-range coupling that can hybridize very largely distant sites. And if we average over many disorder realization, we see that the states are characterized by an exponential decay of the probability distribution at short distance, which is exactly the Anderson exponential tail. Anderson shape of the probability distribution, but at large distance, we have these distance-independent tails that increase with the coupling strength to the cavity mode. The same hybrid shape of the eigenfunction has been observed also in other systems where Anderson localization interplays with correlated long range, and is a general feature that happens via this interplay. We actually can characterize these states as semi-localized by looking at the inverse participation ratio for a fixed value of Q in this case. For example, in the case of standard Anderson localization, we have the extended phase where the eigenfunctions have an inverse participation ratio that decays as 1 over n, so with an exponent tau equal to 1 here. While in the localized phase, the IPR is basically equal to 1 and independent of the system size. In presence of a strong coupling to the cavity field, we have a new phase that emerges here that is characterized by an inverse participation ratio of with a value of about 0.4, so smaller than 1, but independent of the system size. And so we define this phase as semi-localized. The level statistics in this phase is semi-Poissonian, so it's neither Poisson nor Wigner-Dyson, similar to the Anderson transition. And as I'm going to show in a few slides, these states are also multifractal. But before that, I would like to show some effect of these semi-localized states on transport observable. For example, here, if one looks at the return probability, which means we place an excitation on a given site, and then we measure the probability at infinite time that the excitation is still in the initial site, averaging over disorder and all the possible initial sites. Here we have for quick disorder an extended phase with 0 return probability, and for strong disorder a localized phase with return probability equal to 1. And on increasing the coupling strength to the cavity, we have the emergence of a new regime here where the return probability is finite and robust against disorder.
Francesco, hai 5 minuti.
Ok, grazie. This can be seen also in the dynamics through the mean square displacement, that instead of being equal to 0 as in Anderson localization, it grows linearly with time, so it's diffusive-like. And the return probability is related to the inverse of the conductance of the system. So as we have shown here, one can study the one-dimensional system, coupling it at a reservoir on the 2 edges of the system, and compute the current at the steady state. And also in this case, the presence of the coupling to the cavity can introduce a new regime where the conductance is robust against disorder instead of decaying with disorders as expected. And just to briefly mention that if one neglects the nearest neighbor term in the Hamiltonian, some things can be derived analytically. And for example, one can prove that the eigenfunctions are multifractal with multifractal exponents that have this nonlinear dependence on the Q parameter. And it is exactly the same dependence or the same class of multifractality that is observed at the Anderson transition for the system on a Bethe lattice, so on an infinitely dimensional version of the Anderson model. Now, what happens when the density of excitation is finite? We first look at the case without nearest neighbor hopping, which is particularly interesting because it's integrable and so solvable via Bethe ansatz. If the excitation density is small, one can construct the basis by using the single excitation eigenfunction as the excitations of the system, but we are actually interested in the half-filling regime where the excitation density is 50%, so where the effect of interaction cannot be neglected. We focus on a few states that are representative of the behavior on the rest of the spectrum, particularly the ground state, that can roughly be described by a superposition of lower polaritons. The first excited band that can be seen as one dark state and n-1 lower polaritons, and the central band that is where the density of states is maximal, that can be seen as the superposition of different dark states. In the first excited band, the level statistics is semi-Poissonian, so the same that we have seen in the single particle problem. And this can be explained exactly by the structure of these many-body states, because their energy is given by a constant term from the n-1 polaritons, and the randomness comes only from one dark state, so they have the same statistics of the single particle dark states. In the middle of the spectrum, so the vast majority of the states have instead a Poissonian level statistics. So this would suggest that the system seems to be in a localized phase, as Poisson level statistic typically suggests, but instead here it's Poissonian statistic is related to the integrability of the system. In fact, if we look at the eigenfunctions, while the statistics is Poissonian, the eigenfunctions are not localized, but they are multifractal, with multifractal exponents that are, in a sense, more delocalized than the corresponding single particle problem when the coupling strength is large. So we have this contradicting information coming from the level statistics and the fractality of the eigenfunctions. And so we look at transport through the Edwards-Anderson parameter, that is a generalization of the return probability that we studied in a single particle case. This quantity is finite for any value of the coupling strength, extrapolating to larger system sizes, which means that the system does not thermalize. So the system is non-ergodic. So summarizing, for finite excitation density, we have Poissonian level statistics, multifractality, and absence of thermalization, which are all features that are observed in many body localization. But differently from MBL, these characteristics are a consequence of the integrability of the system and are not robust to a perturbation. In fact, if we add a small perturbation via a small nearest neighbor hopping, this breaks integrability, and as a consequence, in the central band, the level statistic changes from Poisson to Wigner-Dyson, and the states change from multifractal to extended. And also the Edwards-Anderson parameter goes from finite to a zero value, so the system changes from non-ergodic to ergodic. So to summarize, I've shown that Anderson localization can be modified when the system is placed inside an optical cavity, and the changes that we've seen are induced by modification in the structure of the dark states, and not so much on the presence of these hybrid polaritonic states. We have controllable parameters that we can play with, specifically the coupling strength to the to the cavity field, but also the excitation density that can allow us to go from the linear regime where the system is multifractal and semi-localized to the finite excitation density regime where the system can be ergodic and thermalizing. There are many possible interesting perspectives that one can look at, for example, the influence of dephasing as opposed to static disorder, or also the effect of transport of charges, so of electronic systems that are a different beast with respect to these spin-like excitons that we have described here. And with this, I thank you all for your attention.
Thank you very much, Francesco. So, questions, comments?
Hi, Francesco.
Ciao, Fausto.
Ciao, ciao.
Ciao, Fausto.
Ciao. I actually I have a questions from when you study the integrable model. Can you show the picture? The Hamiltonian. Okay, here. No?
Yeah.
Okay, now of course, okay, you study this. This is an integrable system, no? And now you consider many different quantity you can solve exactly, and so. And also you show that adding some kind of small interaction, you almost destroy everything, right? If I have well understood. Okay. Yeah, you try only with this kind of integrability breaking, or is there is? I mean, you can try many other which, for instance, doesn't break the symmetry. I mean, do you have some comment to do on the
yes.
kind of integrability breaking? Because of course you can break integrability in many different ways, and but you can keep some symmetry in any
yes. No, that's a good point. We try to break integrability also by making the coupling to the cavity random. So when you have both randomness, both in the spin energies and in the coupling to the cavity, the system is non-integrable. Interestingly enough, if the coupling to the cavity is random, but the spin have a fixed energy, the system is still integrable, but that's just... And well, we observe a similar effect. So we've also broken integrability by a partial randomization of the coupling to the cavity that's been done in a similar work on the Richardson model by having these omega C couplings with the random plus or minus values, and we obtain similar effects.
Okay. In all the cases, you may say that
yes,
it's general. Okay. Okay. Thank you.
It's more clear with the nearest neighbor term, let's say, but it's quite general.
Okay.
Okay. Are there any comments? Okay. If not, we can thank again Francesco and also Julia, and we can give goodbye to everybody, and see you again on this screen on February, the second Thursday of February.